Can you see the slides and hear the voice as well? Okay, great. Good morning, everyone. Thank you, Idli Group, first for the amazing initiative, and I'm very happy to be a part of it and also to talk today about some of the things that I'm very passionate about, which is natural language processing. In particular, I'm going to talk about language understanding, why it is the hardest piece of the AI puzzle. Now, before we begin, let me tell you that this is going to be a very um, basic level discussion or a very top level view of the topic, as in, I won't assume anything about the audience. You may know NLP, you may not know NLP. You should be able to understand most of it. And I also want to give, instead of getting deep into certain technical aspects, I want to cover a wider range of things within the general topic of language understanding. Uh, the reason I chose to keep it like this is because I really don't know how wide the audience will be and what kind of interest people have and background people have. But we can take more specific issues during the question answering, and depending on the interest, we can have one or more sessions where we, delve deeper into various issues of language understanding, very specific issues of language understanding. I forgot to introduce myself. I'm Monojit Chaudhary. I'm a researcher in Microsoft Research India. I have been there for almost 10 years now. My PhD has been from IIT Kharagpur on language evolution, computational models of language evolution. And since then, I have been working on various aspects of language. Okay, so let's start. A very common headline that you have seen these days, on newspapers, on magazines, Facebooks, TVs, everywhere, is something like robots are coming and they are going to take over. So it's the age of AI, and AI is going to win over everybody. Now, here was an interesting article that got published in January this year, which says robots are coming, but you still have the edge. You, meaning the humans, still have the edge. And the same article goes on and analyzes various aspects of, human capabilities, sensory, cognitive, perceptual, neuromotor abilities, and tries to compare where the robots are today or AI is today in comparison with humans, and how it's going to, scale up, how the technology is going to improve over time. So it's trying to make certain predictions. So if you can see the slide, what you can see is on the left-hand side, there are a bunch of abilities grouped under topics like sensory, cognitive capabilities, etc. On the right-hand side, you have predictions. Now, a blue dot means top quartile, a dark blue dot means top quartile human performance. So if you see, recognizing known patterns and categories, information retrieval, gross motor skills, navigation, etc., computers can do as good as the best humans today. On the other hand, the gray dots mean median performance. So things like sensory motor, output articulation, presentation, natural language generation, fine motor skills, robots can do almost like the median human performance today. But what are some of the most challenging things where robots are nowhere even close to us? These are the red blocks where robots are below median, and the predictions you can see on the right. So two things which I want to highlight from here is you see that natural language understanding, it's a red block today, and the prediction is somewhere near 2030, computers will come to median human performance, and to get to the top quartile, it will be 2050 or 2060. That's the prediction. So if you look at the entire chart, the only 2 or 3 kinds of problems which are really very hard according to this prediction or chart is, one is language understanding, one is all sorts of things which include creativity, and the third is social interaction, emotion recognition, etc. Now the other 2 are understandable. Social recognition, emotion, etc., or even creativity are very hard to define. I mean, people don't agree on what is creative. is something beautiful. So these are really hard even to objectively define. Language, on the other hand, can be very objectively defined in most of the situation. If I give you a passage and ask questions from it, and you give me the answers, it's very clear that whether your answers are right or wrong, I will be able to judge. So that way, it's very objective. But why it's still one of the hardest problems? Also, it's interesting to note that we have solved speech recognition very, very well. So Sunaina had presented it last week. So we are doing as good as, it's in the top quartile. Vision, it's in the top quartile. But what makes language understanding difficult and different? So this is what I'm going to talk about today. Now, when we ask why language understanding is so hard, several questions would come to your mind. Like, is it something, I mean, is there something very special about human languages? Do we know how brain would learn and process language? And could we use this to build technology? Is it any different from the way brain processes images and sound? And if so, maybe that's the reason why, you know, there are so much differences between the AI technology today of speech, sound versus language. How do machines do NLP? How the future, I mean, was the future machines would process NLP, I mean, language as, and most importantly, if machines can process one language, let's say English, does it mean machines can process all or any language? Or what does it take to build machines that can process all languages? Now, obviously, all these things are very interesting and people have looked into it. It's impossible to talk about all these things in detail in just one 1 hour talk. So what I'm going to do is talk rather about five sub questions from here. So I will try to address a little bit the fundamental question as what is special about human language? Is there something which is special about human language? Second is, how does language technology work today? I mean, this is very important to understand, because unless we understand that, we cannot follow the last three parts of the talk, which is why language understanding is difficult. And then I will try to make a little bit of connection about how deep learning is impacting NLP and how we see it going forward. You know, how would it revolutionize NLP? And finally, I will touch upon a few interesting problems that has come up because of the situations that we live in today's world, which makes NLP a very fascinating area to work on. There are lots of various other opportunities. And this is where my research also fit in. So I will give you a glimpse of what I do. So let's begin with what is special about human language. So language is a vehicle for communication. And if you think about it a little bit, all species, all biological species, starting all the way from, let's say, bacteria to, insects, birds, reptiles, primates, humans, all of them communicate. Communication is essential for survival. And all of them have certain different kinds of medium to communicate. For instance, insects like ants, and even if you go to organisms like bacteria and all, they mostly use chemical signals to communicate. Whereas birds, dolphins, or even monkeys, primates, they can use vocalization, sound to communicate, almost like humans, but not quite. So something very special happened in the evolution where, we call it the evolution of syntactic communication, where human language significantly diverged from all the other animal languages. And let's try to understand what is the thing, how human language is different from all other kinds of communication. So imagine that I have a sentence, Chomsky is correct. Now I can actually extend it to saying Pinker thinks that Chomsky is correct. Panini once said that Pinker thinks that Chomsky is correct, and so on and so forth. So I can keep extending this sentence as much as I want, almost infinitely. You can imagine doing that, right? And similarly, I can infinitely keep expanding it on the right-hand side. So Chomsky is correct in his assumption that human language is recursive in nature and something. I can do it. So what's special about human language, which at least we don't know any other species on Earth possess today, is that of this recursion. recursion, and because of the power of recursion, we can express arbitrarily complex ideas. So human languages like alarm calls and all often, are restricted to a symbol to a signal. Sorry, a symbol to a meaning. So you could say, an alarm for leopard versus an alarm for eagle versus an alarm for. So different predators might have different alarms, but you cannot combine these alarms to say, okay, there was an eagle here yesterday and tomorrow there might be a lion there that side. So no animal language that we know on Earth can express this kind of, even this kind of complexity. On the other hand, human language has almost boundless capabilities. And compositionality means, not only we can construct these arbitrary strings of complicated words and sentences, but we can also make meaning out of it. How do we make meaning out of it is because we can compose the meanings of the parts to get the meaning of the whole. So this is something very special. And what in mathematical terms, we call it a discrete combinatorial system, as in there are discrete symbols, call them words, call them letters, call them what you want. So various at various levels there are discrete symbols, and these discrete symbols are combined using spatial rules which we call grammar, and they give us structure as well as meaning to human language. So this is something very special, and it's so special, so different from rest of the biological world that Noam Chomsky, even who is the pioneer of this entire, I would say even generative linguistics, or even like modern linguistics, is broadly shaped by the ideas of Noam Chomsky. And we know him in our own computer science theory through this formal language theory, hierarchy of languages, context-free grammar, and all these things. These are all created by Chomsky. So he came up with this idea that if language is so spatial and so different from rest of the biological world, it must be hardwired in the brain. So there is a spatial neural circuitry just to process recursion and composition. Now, this is a highly debatable topic, and for last 30, 40 years, people have been debating. And I don't want to, say what I mean, I can, in another discussion, tell what I believe, which side I'm of this debate, but that's irrelevant for this talk. Where I want to go rather is to how language connects to AI. And the connection was made long time ago, 1950, when AI, the idea of AI started seeding, and the connection was made by Alan Turing himself. So Turing suggested an ultimate test of AI, which all of you here know, so I don't need to go into the detail, which is called the Turing test. So a machine, a human being is chatting. On the other hand, other side, it might be a machine or it might be a computer, and you have to say through chatting that whether it's a machine or a human being. And if the machine can fool the human being to think that it is a human being, then it passes the test. But the fundamental assumption here is chatting, which is essentially natural language communication, is one of the hardest problems of AI. Otherwise, why didn't Turing think of driverless cars, or let's say a robot that can swim, or just speech recognition? So these kind of, or just seeing a face and saying, who is this person, face recognition. So he didn't say any of this. He said chatting. So this actually shows that the idea that language understanding is one of the hardest problems was there itself when Alan Turing himself thought about AI. And therefore, many people started believing that language understanding is an AI complete problem, like NP complete problem. An AI complete problem is a problem. If you can solve it, you can solve any other AI problems easily. So it's one of the hardest problems. And then the other thing is, okay, I will come to that later. So before we proceed to understand why language processing is so hard. I didn't tell you why it is hard. I just said, okay, it is hard. Let's try to understand first how language technology works a little bit. So NLP, again, it was one of the earliest sub-branches of AI, or initially AI was primarily NLP, that also one could say. So the primary aim of this field was to aid human-human interaction, and natural human-machine interaction. So human-machine interaction would be, you can think of your Cortana, Siri, all these digital assistants which you see today are human-machine interaction. If you could, speech recognition synthesis, all are part of voice search, all are part of natural human-machine interaction. The ultimate goal would be if you could program machines using natural language, and many people are working towards that too. So that's one of the primary goals of NLP, how you can make the human-machine interfaces as natural as possible. Then the second is human-human interaction. And here, the obvious thing that might come to your mind is machine translation. So if you don't know, the language of the other person, machine can translate it for you. And machine translation technology is quite advanced today. We also have speech-to-speech translator. So in the Skype translator, one can speak. I mean, I am speaking in English. On the other hand, somebody could, turn on the translator and could hear the same thing in Spanish, for instance. So machine translation is quite an advanced technology today. You may not think of things like editorial tools, spell checking, or grammar checking as NLP tools as such, or an aid for human-human interaction, but they are too. They make your writings more accessible to other humans. A third thing that people do not talk about quite often, and a little less work has gone to it, is NLP can also be used in understanding how language works. It has been almost like a sideline research. So these days with social media, and I will talk more about it towards the last part of the talk, that due to the uprise of social media and a lot of language data, user-generated language data online, today a lot of interesting research is being done, which we call data-driven discovery. So people are trying to understand how human beings use language under various circumstances through machine learning and other things, totally data-driven discoveries. So this is almost like modern linguists in action. Old linguists would take human-human interaction data and manually analyze them. We now can take billions and billions of tweets and automatically analyze them. But essentially, the fundamental question that we are asking is same, that what are the patterns of human-human communication? And similarly, on the other hand, people could also build simulation models of language processes which cannot be directly observed or experimented with, like how language changes over time. It's a very, very slow process, and you cannot really observe it in a day, or not even maybe in 10 years. It might take 100 years. So, but you could formulate models and simulate them and compare the results. So this is one more area where NLP can help linguists, or our fundamental understanding of language. Now, keeping these three goals in mind, let's see how NLP has progressed over the last 50, 60 years. So till 1980s, NLP was primarily rule-based. So I call it the linguists ruled the world. Because if you think of it, linguists essentially look at the data and come up with grammar rules or other kinds of patterns, which are articulated as very clean rules. Like if A happens, then B will happen kind of rules. Now, initially, all the models that people tried to build took a lot of insights from linguists and tried to code these rules in expert systems. Now, the obvious problem with rule-based system is it's not scalable. When you go to a new language, you would need linguists to understand the language of, that language and formulate the rules of that language. So it was pretty clumsy. And when the systems failed, the failure was pretty, it wasn't graceful degradation. So around 1990s, when statistical ideas of statistical learning were already in place, people started applying them to natural languages. But they did use a lot of linguistic insight. So the typical idea was you define very linguistically motivated features and take a little bit of data and learn some statistical rules of disambiguation. So instead of hard rules of disambiguation, you disambiguate using statistical rules that is learned from data. But still, your features were primarily motivated by linguistics. So suppose you want to identify part of speech of a word in a context, you would have looked at the part of speech of the previous word, next word, and whether there's a verb in the sentence following it. And how do you know these are useful? Because linguists know that these are useful. Suddenly something changed around 2000s. So large-scale supervised and unsupervised learning became a reality. At the same time, we also started getting lots of data. So I will talk a lot more about data in just the next slide. But as a result, people started pumping more and more data into these heavy-duty machine learning algorithms and just imagine that it's going to work. And well, it did work in a lot of places. So people thought, okay, linguists have become obsolete and we really don't need to look at linguistics. And it's just important to have enough data. We will solve all problems. So this is what one famous natural NLP scientist, Kevin Knight, said: the pendulum has swung too far. So on the left-hand side, the pendulum that you can see moving. So according to Kevin Knight, earlier days, the pendulum was totally on the linguistic insight side, and it slowly moved. 1990s, 2000, it was probably in the middle, and now it has moved only towards data. And he said a very good thing, because linguistic insight is important. That's his view. But instead of, so he said it around 2010s, let's say, or around that time. But what happened since 2010 is another new technology came, which is deep learning. And what's very interesting about deep learning is you don't even need to define features. So there is no need for features. The system itself learns all the features. So it just totally throws the linguist out of the loop, in a sense. So instead of, Kevin Knight's warning that people should think of more linguistic insight, it went even further and pushed the pendulum further towards data. Now, is that a problem, or we have just solved it? So to understand this, let's see how much data and what kind of data we are talking about here. If you think of rule-based systems in 1950s and 80s, they also needed data, actually. But what kind of data they would need? So let's take 3 example problems to understand. One is part of speech tagging, one is machine translation, and the one is speech recognition, which actually in last talk Sunaina covered in great detail, so you already know how it works, etc. So in post tagging, in 1950s and 1980s, in that period of rule-based thing, you needed very little data, as much data as a linguist would need to analyze and identify the rules, and you would need to test your system. So it was more like very, handcrafted set of test cases designed by an expert who knew that it would cover all the boundary conditions, etc. So that was the style of work. So you didn't need a lot of data, but the data has to be high quality and had to cover a lot of different cases. In 1990s and 2000s, the systems could handle. So for instance, for part of speech tagging, the supervised learning systems would typically need 10,000 to 100,000 annotated words. Now, what do I mean by annotated words? So see on the left-hand side, if you have a sentence, let's say natural language is a fascinating, and for each word, there is a part of speech. So natural is adjective, languages is noun, are is a verb, fascinating is again an adjective. Now, this is what we call part of speech tagging, predicting the tag given the words in context. Now, for supervised learning, you'd need this kind of data. And you'd need hundreds and thousands of words, 100,000 words, let's say, annotated in this fashion. So who would give you this data? There's no easy solution. So you have to train people. So linguists train people how to annotate, and then you pay them, and they annotate. And between 1990s and these 2 decades, or this 1 decade, people have built huge amount of linguistic resource databases. There were like efforts by universities, there were efforts by entire countries, there were consortiums made, and a lot of effort was made towards building these data bases in the US, in Europe, even in India, and almost everywhere in the world to smaller or larger extent. Even companies like Microsoft and Google, who had to build their translation system, they had to build, in translation, you would need the second diagram, block on the left, if you see. So natural language is a fascinating, and it's Chinese translation. So that's a parallel set of sentences. And if you give 10,000 or 100,000 such parallel sentences, earlier days, these systems would work. In the age of big data, these numbers change drastically. So you see there is 1 to 2 order of magnitude higher numbers now we see. Now imagine that if you thought 10,000 words and getting annotated was harder, how are you going to annotate 100,000 words? Sorry, 100 million words now. So it's even harder. Now certain things came to rescue. As I said, one was supervised or semi-supervised learning. The other thing that came to rescue was crowdsourcing, using which people could get a lot of data really cheap. But that really did not solve the problem quite well, and I will tell you why in the next slide. Now with deep learning, the amount of data that's really needed for deep learning is useful because we get better systems, but the systems are only better when you pump in more data. And the kind of data now we are talking about is, let's say for machine translation, 1 million to 1 billion pairs of parallel sentences, or similarly for pause tagging, 1 million to 1 billion annotated words. But we will see if sometimes without that much annotated word, but only words, raw words also help in deep learning, similar to the semi-supervised learning setup in classical machine learning. So this is the amount of data, and how much data do we have? Now here comes the biggest blow. So I did a study back in 2008, and I tried to order the different languages of the world, only the top 20, I suppose, by the number of speakers, their web presence, how much data is there on the web for each of these languages in Wikipedia. And then there is one particular website called LDC. LDC is Linguistic Data Consortium. It's an effort by Penn, University of Pennsylvania. And the idea is to catalog as much data as, all the linguistic resources across various languages that are available there through the website. So I went through the catalog and counted how much data, what kind of data in each of these languages are. And if you look at the figure, it seems there are 4 languages. So first of all, the first observation is there is not much correlation between number of speakers and the other 4 columns. For instance, Hindi is the 5th most spoken language, but if you see, Hindi is nowhere in the web in the top 20. This is top 15 maybe, but even in top 20, it wasn't there. In number of Wikipedia articles, Hindi is nowhere there. LDC Hindi is there, but it's much lower than 5th. It's probably 10th or 12th. So don't worry about the 2 columns, LDCI and LDCW. There is almost the same thing, calculated slightly differently. So there is a big skew between the number of speakers and the amount of resources there is. Moreover, if you had drawn the curve, which I'm not showing here, of how much resources, it's a power law distribution. So English, Arabic, Chinese, and Spanish has a whole lot of resources, but all the other languages, they drastically fall below, it's like almost 1/10 of the resources that all these languages have, you would see in Japanese and Korean and German and French. And then if you go to Czech, Portuguese, it will be further, 1/100 of these resources. And English is by far actually bigger, even larger than Arabic, Chinese, and Spanish. So now one interesting question for you to think about. So why English, Arabic, Chinese, Spanish? What's special about these languages? Now, one thing you could see is, of course, these are also highest spoken languages. So Mandarin, Spanish, English, and Arabic are the most spoken languages in the world. But is there any other reason? My hypothesis is that these are the languages which either are spoken in the US or US is scared of. Okay. So let's go to, okay, it's to summarize, right? So language technology has progressed quite a bit, and we do see that it's primarily data driven. All this is good. Linguists are no longer cared for, which probably is okay. If you think from a practical point, you would only use things which you need. So if linguistic knowledge is not required, okay, fine. But then the biggest problem is the data skew. The languages which don't have data, the data gap was already high. With deep learning, which requires more data, there is almost no hope for languages like Hindi and all, because when on earth you are going to create so much of data for them? So this is a very sad state of affairs, and I can go on talking about it more and more. But let me switch gears here and come back to the question that I had posed in the beginning, that why language understanding is so difficult. So to understand this, let's look at a conversation. So this is a conversation happening between Rahul and a computer that, let's say, somebody has, designed to pass the Turing test. And this is a hypothetical conversation, by the way. It's not a real data. But this is something very natural in human-computer interaction. These kind of things are very natural. So Rahul said, I saw a monkey with a banana. And the computer said, oh, that's gruesome. Now, can you think why that's gruesome? What's gruesome in the sentence, I saw a monkey with a banana? So it happens to be the case that saw is also the past, is also the present tense of the verb of sawing. Sawing means cutting somebody with a saw. So the computer parsed this sentence as Rahul said he cut a monkey into pieces using a banana. So I saw a monkey with a banana. It's similar to I cut a cake with a knife. Of course, that's a possible interpretation, but we would never think of it. So Rahul says, why? What's so gruesome about seeing a monkey? Now the computer gets, oh, he's talking of seeing a monkey and not sawing a monkey. So computer gets that and then says, oh, I see. And then it says, what else did you see with the banana? Now computer does another mistake. So computer thinks, Rahul said, I saw a monkey with a telescope kind of a thing. I saw a monkey with a banana. So banana is an instrument like the telescope. So that's why it's asked, what else did you see with the banana? And so on and so forth. So if you think of it, what's happening here? There is ambiguity everywhere in natural language. The words can mean multiple things. So saw can mean 2 different things here, right? There are words which can mean 20 different things. Almost every word which like about has 5 or 6 different usages in English, right? So about could mean approximate, about could mean, in the context of something, I'm about to do this. So it's like a near future. So every word actually has so many meanings, but we never even think of those things. We just automatically process them. So natural languages are full of ambiguities, and somehow human brains are conditioned. We are conditioned in such a way that most of the time we don't find it difficult. But if you build a computer which actually tries to apply the rules of grammar, etc., to interpret, obviously the ambiguities will be very clear. Now, why do we resolve the ambiguity? How do we resolve the ambiguity automatically? The thing is, first of all, frequency. Words like saw, using saw as a verb, saw as in the instrument saw, is much less frequent than using saw as the past tense of see. So frequency is one. When you are talking of monkeys, bananas, in that context, automatically sawing a monkey with a banana doesn't make sense. Banana is not even an instrument for sawing. If you say, I saw a monkey with a banana, you would not have thought banana is an instrument of even seeing. So the monkey must have had the banana. So what is all these things? Where are they all coming from? So these are what we call the world knowledge or the common sense. So what are different kinds of knowledge that implicitly goes in language processing? So first of all, of course, linguistic knowledge. You have to know the grammar. You have to know the words and their meanings. But not only that, you have to know idioms. So if I said he kicked the bucket, it really doesn't mean he literally kicked the bucket. It's an idiom which means somebody is dead or something, right? So similarly, proverbs. Then metaphors. So when we say, oh, the city doesn't sleep, it's really not that, I mean, that city is an individual which was supposed to go to sleep, right? So these kind of things are abundant in language everywhere, and we have to know how to process them. The second thing in language is pragmatics. Pragmatics is very hard. I will tell you what pragmatics is with a couple of examples. So pragmatics kick in after semantics. So semantics give you the literal meaning of the sentence, but then pragmatics tell you how to interpret this particular sentence in this context. Let's take an example. So somebody might say, it's very hot out here today. And suppose you are sitting next to the fan, and the fan is off actually. So most likely you would probably go and switch on the fan. So that's my implication when I say, it's very hot out here. So it's a polite way of saying, can you please switch on the fan instead of that, right? Now imagine I had said, can you please switch on the fan? You understood the sentence and you said, yes, I can, and didn't do anything. Now you're correct. Linguistically, it's perfectly meaningful. I told you to, I asked you a question whether you are able to, and you said I am able to. But that wasn't the intention, right? It was a request. So in that context, it was a request. So that's where pragmatics come into play. So understanding in that context. And that's why if you see chatbots these days, I mean, if you imagine any conversation would require knowledge of pragmatics. Otherwise, the conversation would not go far. And that's why building realistic chatbots which can engage a user in a good chat is so hard. And sometimes this includes actually a lot of context, not only the immediate context, but what you had said 10 days ago. To me, I might apply in today's chat context. So this is pragmatics. Probably I have a few more examples later I will talk about. Second is world knowledge. So let me give you this t-shirt example. So I'm a huge metal fan. And there is a fan, photo of a metal fan. Now, this is supposed to be a funny t-shirt. Now, the only way you'd get that it is funny is if you knew that metal is a music style. And metal fan would mean, in this case, I mean, I'm a huge metal fan typically would mean that I am a big fan of this class of music, which is called metal. But you are putting it with a big metal fan, and that's funny here. So the fact that metal is a class of music, genre of music, is basically a world knowledge. And to interpret puns, sarcasm, a lot of different things, even like day-to-day language, would require a lot of world knowledge. Then contextual knowledge. So this is another example which I'm sure most of you would have seen. So this is a geometry question. And it asks, find X, and it says, the student says, here it is. Now the question is the student wrong? I mean, why is it funny? Now, of course, the student is not wrong. Find X, well, there is X. But in this current context, that's not what the intention of the teacher was when the teacher said, find X. So that's contextual knowledge. And then, most importantly, there are also socio-cultural norms which sometimes create many weird situations. So I'm sure a lot of you, when you meet people from a completely different social background, it could be in India itself, or especially when you go outside, you would have sometimes weird conversation exchange or body language exchange, and later you would have interesting stories to tell about it. So let me ask you a question here. Let me tell you a situation. Suppose you are going to, you have submitted an application to your professor, and your professor needs to sign it so that your leave is granted. Your professor forgot to sign it. So you go to your professor and say, sir, may I ask you to please sign that? And second way of saying it is, sir, may I request you to please sign that? Which one would you use, ask or request? Now, when I asked this to, in other places where I was giving the talk in India, when I asked this, most of the time the answer is, we will say request, because it's impolite to ask a professor to do something. It's almost like an order, right? So I should actually, because of the social context here, the norm would be to request the professor rather than ask the professor to help you. Now, interestingly, this is very geography dependent. This is not true everywhere in the world. In the US, it's just the opposite. So if you search for whether to use ask or request on Quora, you will get this kind of answers. So you'd see things like request is much more formal and polite word than ask. So you would use request only if it's a very formulaic, usage. So professor in the US is not that formal relationship. A much more formal would be a legal lawyer talking to a judge and those kind of situations, right? So those are formal. I mean, when you are talking to your professor, it's not really that formal a situation. So why would you say request? It would mean that you are distancing yourself from the professor. Even people go so far saying that, in my mind, it is rude to request something, almost like you are demanding it. You should rather ask. So ask is a polite way of saying this. So see how interesting it is. The same language we are talking about, which is English, and the same two sets of words, and everybody thinks that request is a politer version of ask, yet in the given situation, which one you should use varies so widely between the cultures. And there are many, 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 many such examples. So you can imagine how hard it would be then to make a chatbot which would satisfy everybody everywhere in the world following their norms. So either you build chatbots specific to geographies so that they can follow the norms and have those inbuilt politeness things, or if it's a general thing, I don't know, God save it. So this is another aspect of language, which is, so let me tell you this, that pragmatics, so all the things that I talked about, world knowledge, linguistic knowledge, of course, we know how to process it, but pragmatics, contextual knowledge, socio-cultural norms, especially pragmatics and socio-cultural norms, are certain things that we have just started to understand, meaning computationally model, and started working on these. So it's a very, very recent area of work within language understanding. So this is the first reason why language is hard, that it requires common sense. Second reason why language understanding is hard is that language is dynamic. Language is dynamic because it always changes. So here is an example. So after Trump became the president, or maybe before Trump became the president, there was this, somebody published this list of words and their meanings. And I'm sure some of them might have already become commonplace in social media. So Trumpisms. So these are all new words and human beings can very easily understand it. But imagine, a machine to understand this just from the definition or just from the context, it would have never seen it before. Another example of how language changes. So you would have heard such expressions very commonly. He was like, why she didn't like his profile pic. Now, what is the first like here? It's not any sense of like that an English dictionary would define. This is like, this like is essentially he was saying why she didn't like. The second like is also something which any English dictionary would not define, because this like is a new usage that came up with Facebook and then now popular all over the world, in also not Facebook, but other forums. So, so in this way, new words assume new senses, new words are coined all the time in language. By the way, Steven Pinker wrote a very interesting article which says 10 grammar rules which are okay to break. And one of the things was about like. And if you see the ad on the right-hand side, it says, Winston tastes good like a cigarette should. And this ad, which was, I think, first time published in 1920 or sometime, I don't know when exactly. At that time, they had said, oh my God, the slogan is grammatically incorrect. Now think about it. Is it grammatically incorrect? Winston tastes good like a cigarette should. It turns out that it is grammatically incorrect because in those days, like could not connect to verb phrases. So Winston tastes good is a sentence and the cigarette should is a verb phrase. I mean, also has a verb. So it could not connect to verb. It could only connect noun. Like, X is like Y, where X and Y are both nouns. But today we won't even recognize because English has changed enough since then. And this is very much like part of the language. The third thing, which I will go in much more detail in the next part of the talk, is I already said language is a discrete combinatorial system. And it makes language processing very hard. So if you see, speech is a continuous signal. If you see, image is a continuous signal. So this is the building one, it's the image of IISc. the main building. And if you move this building slowly, I mean, essentially you are not moving the building, you are moving the camera slowly. Or if you apply some filters slowly, the image will continuously morph from, let's say, the top one to the bottom one. So in that sense, image signal, speech signal, these are continuous signal. Language, on the other hand, there is no way to change one word slowly from one to another. If you even make change in one letter, so if you make cat into a mat, it's completely different in the meaning space. So it's very hard, and that's where the neural networks are interesting in the context of language. To give another example, right? If you have how to recognize speech, and a computer recognizes it as how to rake a nice beach. Now, obviously, there is very little difference as far as the phoneme sequences are concerned in the two. But if your speech recognizer did the second one, how to rake a nice beach, it makes absolutely no sense. Or rather, the distance from the first one and between the first and the second two sentences is huge. It's not a subtle change. So this is a very inherent property of discrete combinatorial systems. Since it's not a continuous thing, a small change can make a big change in the meaning or output, a small change in the structure. So in general, as I just reiterate, that language understanding is very hard because you need common sense, you need understand socio-cultural norms, lots of different things. So therefore, it's almost like solving the general intelligence problem, even though you are only solving language. And that's why probably it is AI complete. And recently, Bill Gates made this comment that he believes the biggest breakthrough in AI will be when computers can read and understand information like humans do. Okay, so now I'm moving to the last two parts. I will get into the deep learning part. Before that, let me quickly check the time. So we have probably 10 minutes. Okay, so I will quickly wrap it up. So in the context of deep learning, right, has deep learning changed NLP? Now, there are various tasks in which deep learning has really helped NLP. So like classification, sequence-to-sequence mapping, structured prediction, condition generation, so machine translation, all these things. One specific thing in the context of NLP and deep learning people do is multitask learning, where you train a network to do more than one thing. Let's say part of speech tagging, named entity recognition, language identification, and transliteration, all the things at the same time. So such networks sometimes are better because it actually cross-feeds. So it learns from, the network learns from all the tasks and can reap the benefit of all of these structures simultaneously. So it has helped. But how has it helped? Is it like something revolutionarily different, or is it like, a percentage improvement in the accuracy? So in most of the cases, right, it's a percentage improvement, which is not very exciting. It's just like, okay, yet another technique that solves the problem a little better maybe, but well, you have to pump in more data, etc. But there are interesting observations. For instance, when you do machine translation, you find that in German English, there is almost no gain compared to earlier method, which is phrase-based machine translation, whereas for Japanese English, there is a substantial gain. Now, why this is so? Why neural machine translations are able to handle Japanese English much better than German English? So to answer this question, let's try to understand how neural networks work. So neural networks, in a sense, are universal approximators. So it can approximate any continuous function. And I just said that language is not a continuous function. So it's a discrete combinatorial system. So in that sense, neural networks actually should not help language processing much. But turns out there are two reasons why deep learning has fundamentally helped NLP. So one is it helps in modeling infinite context. So whenever you are looking, I told you that, whenever you are trying to process something, it's not process a chat. It's not that past 2 turns, 3 turns, 5 turns matter. What you might have said 10 turns before matters. When you are translating a sentence, not the left word or right word matters. All the words, I mean words which come maybe after 10 words also matter. So traditional NLP techniques fumble to capture these long range dependencies. But with RNN kind of things, you can actually potentially remember infinite context. and RNN coupled with LSTM, right? So it can remember potentially infinite amount of context. So this is one thing which has really benefited NLP. And this is why Japanese English translations are so better with Neural MT, because Japanese English word orders are different. So it's like Hindi English. So Hindi, in English you say I ate my food. In Hindi you'll say maine khana khaya. So you see food and khana, khaya. So eat and food, the order is reversed. So Japanese English has lots of these ordering changes. So therefore something which might occur in the beginning of the English sentence might occur at the end of the Japanese sentence. This is not true for German English. They are almost similar word order, exactly same word order probably. So therefore phrase-based MT can do better, but long distance dependencies and understanding where is needed, phrase-based MT fails and Neural MT helps. The other very, very important thing is word2vec, a very, very important innovation in the case of NLP. Well, see, when you have a word, and as I said, if you change the word subtly by character, the meaning doesn't change subtly. It jumps from here to there, right? I mean, in the meaning space, if you can imagine, the meaning actually the meaning of cat and mat are not related. So how do you represent the meaning in a continuous form? Now, again, this is an old problem, and people have tried other techniques like latent semantic analysis and stuff like that. So neural network gives us another technique, which is word embedding or word2vec. And it turns out that word2vec works very, very well. And it generalizes so well that you can learn from large corpora about how to, take the discrete words and map them to a continuous space of meaning. Now, once you map them to a continuous space of meaning, a vector space, you can do all sorts of things. You can add words like you do in continuous bag of words model. You could, add words in a weighted way like you do in, let's say, skipgrams, or you could maintain position and add words. So you can do all sorts of geometric operations. And therefore, a lot of things give us interesting results. I'll skip this image of word2vec. Many of you might be already aware of it. But then deep learning doesn't solve everything. Deep learning does not tell you how to integrate and do common sense reasoning. And this is the biggest bottleneck today. Why? And that is why the predictions still say that why language understanding will take so much time before we solve it. See, in deep learning, it's not clear how to integrate an external knowledge source, how to store learned information. So during the conversation, you will also learn information. So how can you store it explicitly, and how to reason over that knowledge base explicitly? So somebody might argue, why to do all these things explicitly? The network weights will do it. Yes, true, the network's weight will do it. But imagine the size of the network that you'd need and the amount of training time that you'd need to train if you had to give it all the world's knowledge. On the other hand, you could represent the world knowledge in terms of more traditional ontologies much more easily. And then you could actually use the deep learning to reason on the ontology plus the current context to generate the best possible output. Now, this is an open research area. And just 2 days back, somebody from Yoshua Bengio's team had come to MSR and gave a talk that they're working on this. I would be very excited to see what's coming out of this. Okay, and this last bit, why right now NLP is a fascinating field of study. I will very quickly, maybe in 2 minutes, I will try to wrap up. So what has happened in the recent times, last 10 years or so, is that we have now lots and lots of language data. So this data primarily comes from user-generated content, from social media, from the web. There are some stats which shows that the data is humongous. It has all sorts of variety. And the other interesting thing is that this data is socially grounded. So you know a lot of things about the data. First of all, speech data is very expensive to collect, but social media data is almost speech-like. You write almost the way you speak. Then you could get a peek on people's personal conversation. It's socially grounded in the sense that you know the demography of the person posting it, the social relationship between the people talking, etc., from their network. And then you can also study things like how language evolves, like how hashtags evolve, how spelling changes, how something becomes a trending topic. All these interesting things can be studied. So this has spawned a lot of interest, and a new field of study has come out of it: computational sociolinguistics. which actually tries to study this politeness norms and all this, group behavior, in-group behavior, out-group behavior, how people use language to mark boundaries of groups, etc. So all these studies can be now done at large scale in data-driven fashion, thanks to social media data. So we also do a little bit of this work in Project Melange. So that's the photo of the team of Project Melange. So we have been working for 2-3 years. So one of the 3 years now. So one of the things which we are interested in is language mixing. So people mix language and in multilingual communities in the same conversation, like if Indians mix English, Hindi, English, Bangla, English, Tamil, all languages are mixed with English. Sometimes 3 languages are mixed. So our aim is basically to understand the structure. This is called code switching. So we want to understand the structure, the extent of code switching function, and then how to tackle code switching in, let's say, translation, speech recognition, and all these things. So I just want to tell you one study very quickly, which we did recently, which shows the power of the current machine learning techniques when coupled with the social media data, what interesting things we can do. So people switch language. So if you imagine English, Hindi bilinguals, when they tweet, they would switch language between English and Hindi. But the question is, when do they switch? And is there a preference for a particular language? Now, there are these tweets that are taken from, these are real tweets by people on some topics of politics and movies, etc. And if you see, people have tweeted in both English and Hindi. Now, do you see a pattern here? It so turns out that there are various patterns, but one of the patterns that we looked at here, the pattern that prominently came out is that people in India switch to Hindi when they want to express a strong negative sentiment. So we might praise you in English, but gali to Hindi mein hi denge. So all the swear words, or 95% of the cases, the swear words were in Hindi. Although there are also gender effects. So women tend to swear more in English, but men tend to swear more in Hindi. So there are linguistic theories which says that for emotional expression, people prefer to use native language. And indeed, we do observe this, at least in this particular case, we did see. Okay, so let me wrap up with this. And the takeaways of this talk, as I said, it's going to be a very high-level talk. So I tried to cover a lot of things. So I said why human language is spatial due to its recursive nature and discrete combinatorial structures. I tried to sell the point that language understanding is a hard problem and why it is a hard problem. I hope the message got across and you are sold on it. Deep learning does hold a lot of promise, some promises, especially in terms of Word2Vec and other things, but it doesn't solve the core problem, which is the common sense reasoning and how to integrate it with the language processing. So that's still an open problem. And then I also want to leave you with this message that language technology is primarily data-driven, which has a lot of benefits. But mind you, if your language has no data, then your language would never show up on the technology map. And that would affect the progress of the entire community, linguistic community. And most of the languages today in the world has very little data. So this is, I think, quite an alarming situation, and something needs to be done about it. So even if we solve the problem of language understanding in, let's say, next 3-4 decades, as the prediction says, we would solve it only for English or maybe 4 or 5 languages of the world. For all the major languages of the world, it's going to take a century, unless we can do brain reading and tap entire language information from a native speaker's brain to a machine. With that, thank you. And I can take questions. I know I'm a little out of time, but I can spend another half an hour easily. So it's fine with me. Okay, so I see there is one question. What is Zipfian barrier of NLP? So you must have read from the slide title. That was the sorry, the subtitle in the slide. That was the title of my talk. So Zipf's law is a law in language word distribution in languages, which says that if you take the words of if you take a large corpus and count how many times each word occurs, that is the frequency distribution of the words, and plot them as follows, that on the x-axis you plot the rank of the words, so the most frequent, the second most frequent, and so on y-axis the actual frequencies, then it follows a power law with an exponent of -1. So in other words, frequency is proportionate to rank to the power -1. Or frequency is inversely proportionate to the rank. So what it means is actually very quickly you see a drop. So there are 20% of the words, or maybe just handful of words which covers most of the corpus, but there is a long tail of words which doesn't cover. Which occur very less frequently. So this is a fundamental problem in NLP, because you do not get to see words enough time to learn from it, no matter how large a corpus you get. Even then Zipf's law will be valid, and there will be words which you would not have seen it. So this is called the Zipfian barrier of NLP, and I try to apply it in the context of resources. Even in resources, you see certain languages take all the resources, and most of the world's languages do not have any resources. So even when you solve NLP, you solve it only for some languages, you still don't overcome the Zipfian barrier. Has anyone done a large-scale successful Turing test? Okay, so there was a news, I think a year ago, that some particular machine passed Turing test. Now, I will tell you how the Turing test happens. In fact, I encourage you to go to a website. You search with Loebner Prize, and you go to a Loebner, L-O-E-B-N-E-R. So you go to the website, and you would see the rules of the contest. So essentially, you have to design a bot, and you have to give it a personality. So you say that, okay, this is a 30-year-old American woman, and you are chatting with her. So, and then and of course, it should answer accordingly. So if somebody asks, what is your age? It should say 30. Now, since there was an option to set the personality, as far as I remember, some people did a trick. They said it's a 13-year-old Ukrainian kid who knows very little English, and the chatting was in English. So all the errors, so it could fool the judges, because it was, so the judges have to chat for a certain amount of time, and it has to fool 3 out of 5 judges, or engage the judges for such. So there are some rules like this. So essentially what I'm trying to say is, under that well-defined competition, yes, somebody has passed. But that doesn't mean much, because it was just more like exploiting a loophole in the way the competition was defined. But nobody has passed a full-blown Turing test. The best digital, chatbots that you see around are probably Siri, Cortana, and this Google Now, and likewise things. And you know how bad they are, right? There's no question of passing the Turing test. So the other question is, we have a lot of TV serials and movies in Hindi. Can't we just do speech to text for them and use them as a corpus? So this is a good question, actually, and people have been trying to do this. For instance, we do at Microsoft, we do try to get contract, get into agreement with, let's say, this Z Group or somebody. I'm not saying we went into a contract with Z Group, but something similar with some groups. And then we can take all their recordings and then try to train. The script is also there. So there are a couple of issues, though, and I think Sunaina is a better person to answer this, but somebody who works in speech is a better person to answer this. But as long as I know, as much as I understand, acted speech and natural speech are very different. So even if you get a lot of data and train, it turns out when you run it in the wild, the accuracies are much lower. And if you could collect speech from the wild, even much less, let's say 1/10 of the recorded acted speech, you would still do better in the wild. So there's a big mismatch on how the dialogues are delivered, the noise quality, and all the things. Having said that, yeah, that's a good idea, and people have tried doing that to some extent. Like YouTube is another source from where people can take the audio and the subtitles and learn from that. And I know people do that kind of things. Then there's IBM Watson used a lot of rule-based techniques for answer determination. Do you think for language with less data, a mix of automatic and then manually corrected rule-based ontologies might help? Certainly true. I will give you a very concrete example. So speech technology, almost everywhere you use neural nets, right? I mean, that's the state of the art. But if you think of a new language, let's say we want to build a speech recognizer for Tulu from the scratch, I would never even think about neural networks because the amount of data it would require is huge, right? So you try to build a speech recognizer first using traditional techniques, let's say HMMs and all. It will work. It won't work very well, but if you were trying neural network, it would have worked even worse with that much of data. So it would work to some extent, and then you put it in the wild. As people use it, you get more data, and then eventually you will gather enough data. So that has been the strategy of most companies when they expand to new languages, that they put something out there quickly. Google is an expert of that strategy, right? Google has been doing it all the time. So initially they put not so great systems, but over time as people use it, they have a lot more data, and with that data, the systems also become great. So this is one. So you can use traditional, and you should use actually traditional techniques. Now, in particular about the rule-based things, yes, I mean, most of the Indian language techniques that exist today, for instance, are rule-based. Even there are translation systems in between Indian languages which are rule-based and work to some extent. So, so that's one way to go, I would say. But the thing is, there is no very clear strategy from taking that rule-based system and suddenly, getting more data. Like the Google model that I just said, right? Put out something and it will become successful, you get more data. Doesn't quite hold true. Probably Google has been able to replicate it, but I can't imagine a professor, sitting in an Indian academia doing it and replicating it. So that's one hurdle there. So how is reinforcement learning used in NLP and NLU? So reinforcement learning is used a lot in chatbot training. So imagine that you are, so let me tell you how chatbots are trained. So there are two kinds of chatbots. One are called these digital assistants, which are like Cortana, Siri kind of things. And they are rule-based primarily because they have to solve real tasks, and you have to understand what exactly the user said. Like book a ticket means, you have to ask which, from where to where, etc., etc. So these are dialogue. This dialogue planning is done. There are state machines, huge state machines with all these dialogue plans, recoveries, error recoveries, and everything in place. So that's how the traditional dialogue systems are built. But when you want a chatbot which just engages in useless chit chat, so for those kind of things, and don't ask me who would use them. Apparently, youths are crazy about them. So in China, Microsoft released a chatbot called Xiaowise, and there was a huge, I mean, it attracted a lot of people, and a lot of people even fall in love with Xiaowise. So it's I don't know how that psychology works. Now, okay, so how these are trained? You take lots of human chat logs, and then you look at the 3 or 4 or n number of previous turns. You feed them in an RNN kind of a setup, and let it generate the next turn, which the machine is going to say. So this is broadly the architecture, and you train these models, deep models there. Now, what happens is there is no good yes and no here. So if I say, how are you? There is no one correct answer, right? There are lots of ways you can answer this. So how do you evaluate? So the way to do it is reinforcement learning. So if I ask you, how are you? And you say, I'm good, I'll say, great. That's a good answer. You say, I'm not good, I will also say, great. That's a reasonable answer. But if you say, my name is blah, I will say, no, that's not a good answer. So in this way, you can reinforce, and it over time learns. So I think chatbots are one where reinforcement learning is used a lot these days. And there's a lot of scope too. So there are two questions. One is, can you give an insight into how to go about developing NLP techniques for under-resourced languages? Like I already said, right? So somebody pointed out in the right thing. So for under-resourced languages, classical techniques would still work better, would be the way to go. So for certain things, also, certain things like morphology, part of speech tagging, morphological analysis, where given a word, you want to identify what suffixes, prefixes it has, and what do they mean, etc. So these can be built. I mean, rule-based systems can be built for them. But for some other things, people have seen, like speech is one example, but even in NLP, like when it comes to, let's say, translation and all, unless the languages are very close to each other, like say Tamil, let's say Telugu and Kannada. So unless the languages are like that, rule-based system doesn't perform well. So you need to build some resources. Crowdsourcing helps only so much. Now, depends on how many talkers you would find in your language. So fortunately, in Indian languages, if you want to do something, crowdsourcing helps because a lot of talkers are from India. But even like we were trying some things with Norwegian, and we didn't find enough talkers. So crowdsourcing can help in certain situations and doesn't in some other. Of course, at some level, you have to, to bootstrap, you have to also pay and build some basic resources. Then there are a variety of techniques, which is one technique is called piggybacking on some other language which is close by. So suppose you want to build things for Marathi. You don't have enough things for Marathi, but you have lots of data for Hindi. So there has been work on how you can adapt, learn things from Hindi and adapt it to Marathi with little bit of Marathi data. So I think lots of things are there, but there is nothing which is greatly successful. Or in other words, at the end, it does pay you to, invest a lot and build very good and large data sets. Even unsupervised, even raw data sets are useful. If you can collect a lot of raw text corpus in a language, it's useful. Then there's a question on, do you consider code mixed Hindi-English as a new separate language, considering that in some cases the grammatical structure changed? Wow, so this is a very, very interesting question, and I don't have a short answer to it. Let me just tell you that linguists would not consider it as a new language, and they have been talking about how the grammar of the two languages can interact to give a hybrid grammar. There are well-known models which can take grammars of two languages and make a hybrid grammar. And it's pretty common. English Hindi is not an exception. It happens with all Indian languages in English. It happens with English Turkish. It happens with English Spanish. So languages which get very strongly integrated, where you can switch even at suffix prefix level. So you can actually define a hybrid grammar for that. But what model works for what language? Is there a universal model and all? These are the questions which are open, and we are working on some of those. So let me not delve into that. That will be too long a discussion. Maybe another talk we can discuss this. But having said that, there has been a recent paper which says that, well, English, Hindi plus English, is probably a new language, not only because of the grammatical reason, structural reason that you are talking about, but also for a social reason, in the sense that there is a generation of urban Indian speakers who cannot speak Hindi or English alone as a monolingual, Hindi monolingual English. They are speakers of English. That's what they grew up learning. That's their native language. So from a social perspective, probably English is a new language. So I don't want to get into that debate. I will just leave it there with some, with some food for thought. And our work has mostly tried to, so we have been trying to look at how we can use the monolingual resources as much as possible without building fresh resources in English, but using monolingual resources make systems that work for English. So that is our goal, and we have been fairly successful doing that. Because if we think English is a new language and start building resources in English again from scratch and all, we are not using all the Hindi and English resources that's there and that could be used. Okay, let me go to the next question. How to decide between end-to-end conversation agents and traditionally separate components such as intent, understanding engine, dialogue manager, and intuitions on choice? I'm not sure if I get the question here in the sense of whether the decision is while you are building a system. I mean, in the sense that you want to build a conversation agent and you want to see where these components fit in, or it's a question of whether the conversation, whether is it a choice between a conversation agent versus these various different systems. Oh, okay, I think I got your question. You are trying to say like the neural network based conversation that I talked about, where you just train with the previous turns and generate the next turn. So that's one end-to-end conversation system versus you have a case where you separately understand the intent, then you have a dialogue manager, and then you generate the natural language, right? So when to make which choice? Okay, so if that is the question, I think the answer is, so currently, if you really want to solve any task, it might be booking a ticket, it might be giving information about something. The only way we know we do these things better is by intent understanding, dialogue manager, and NLG. Because there, you cannot do errors. If you make errors, there should be an error recovery loop. And in the end-to-end conversation systems, we don't know how to actually work out error recovery loops and other things. So all the task-oriented systems are right now based on this classical method, I mean, reductionist method. Whereas if you want to do this end-to-end one-shot thing, they have only been successful in, useless chat, purposeless chat. Let's not say useless, purposeless chat. So if you just want to engage somebody in a chat, those systems are fine because they cannot actually stick to topic. They cannot actually, use information from the rest of the world and connect them. So all these things are not yet done. So that's what was I was trying to say when I said we have it's still an open problem how you integrate the knowledge, contextual knowledge, world knowledge, and intent and pragmatics with this end-to-end conversation system kind of things. Yeah, I think I have answered. I mean, I got the question clarification. Yeah, but I think that's what I understood. So I answered that. There's another question: is traditional NLP approaches useful for tasks like visual question answering? Visual question answering. So visual question answering is about an image. I mean, I don't know. Let me just say what I think visual question answering is. So you show an image and ask questions about the image, and you have to answer. So does this image has a cat? Is an easy question. A harder question would be, is the person in this image sad or happy, or is he walking towards left and doing something? So that would be a VQA, I guess. So is traditional NLP approaches useful for the task? I think traditional NLP approaches are applied at various levels. So when you train VQA systems, you have the visual, you have the question, and you have the answer. So of course, you parse the image using image processing techniques. And there are two ways of doing it. I think most of them, I don't know much about it, I must admit, but most of the systems probably try to map the language and the image into the same subspace, same space, so that it's easy to move between the language and the image. I mean, whatever concepts are there in the image and the concepts there, it's a cat in the image and cat in the language, so they can be easily merged. Now, when you are training the system on the NLP side, on the language side, you do lots of processing which are very akin to NLP. Similarly, when answering, right, the question itself and the answer generation, etc., would be probably using NLP. But whether the scene parsing requires any NLP technique, I don't think people would have used it. Yeah, so I'm not sure if anybody has used it. I haven't seen. But I have seen interesting work, like people have taken a set of images, and the task is to, so it's a story. So you have to understand the images and reorder them in the sequence of the story and write the story. So the task is to reorder the images and write the story. So yeah, I mean, you could look at work by Devi Parekh and Professor Batra. I forgot, Dhruv Batra, I think. They have done a lot of interesting stuff on this direction. Okay, so I think there are no more questions. So thank you all for attending and asking lots of interesting questions. I know, I mean, the talk was a little on the high level side, but if you guys are interested in more towards code switching, what we are exactly doing, or any other particular topic in NLP, if you want to delve deeper, I'd be happy to give more talks. Or I mean, you're most welcome to check our Melange website, and there are papers which talk about some of the work that we are doing right now. Okay, thank you.